Good morning. Welcome to Physics STPM. Cambridge A-level students can also find it useful. Down the notes. Okay, let's go to the syllabus. It's 1.4, Uncertainties and Measurement. Calculate the uncertainty in derived quantity. Rigorous statistical treatment is not required. Write a derived quantity to an approximate number of significant figure. Okay, let us make a start. Right, this is the Cambridge A-level AS syllabus 9702. Under 1.3, scalars and vectors. Only this topic I don't cover. Right? Other than that, this topic also didn't cover, covering only this part, number 3. Okay, measurement. Right? Earlier topic, you look at quantities and unit. But now, this topic we are looking at each quantity that we measure, there is an uncertainty there. Like the speed of car is 60 km per hour. We want to learn how to write the number of significant figure. We don't want to write so many significant figure, unnecessary. Topic 2 onwards, we are going to look at other quantities, other derived quantities, and we will define it like speed, a derived quantity. Remember, potholes start from a depression on the ground. A depression on the surface, and if on sand, it disappears after some time because of rain or wind, cover the depression. Become bigger and bigger if the car keep on going over it, different cars going over the same pothole, and then it become an incident. The driver of the car will remember for whole life when the pothole is too large. Right? To learn physics, cannot learn by reading or studying. You reinforce your understanding by solving problems. For every topic, remember to try the past year paper. If got problem, you can ask a teacher in class. Okay, let's go to significant figure. Right? This is the first one that we count. This 20 we don't count. Right? This 0 between the number we count. So it's 3 significant figure. Correct to the number of significant figure. Right? As I said, the 20 here we don't count. We count it as one significant figure. This is also one significant figure. This is 2 significant figure. We write inside there because we want it counted. Depend on the instrument that we use. Same as this one. This is 3 significant figure. The 20 is counted. This 20 is not counted. Right? Or we can summarize 0 before a number other than 0 is not counted. And there's a number. 0 before, we don't count that one. We don't count this one. Count this one. Right? Usually it's the instrument that we use for measurement that determine the number of decimal place or number of significant figure. Right? Let's know how to correct the number of significant figure. This is 4 significant figure. This is not sure. Right? It can be 1, it can be 2. This one is for sure because you add the 0 in because it can measure up to that 4 significant figure. Right? 1000, we don't know how many significant figure. It can be 1, it can be 2, it can be 3, it can be 4. Right? So you want it to be clearer. One significant figure, right, as that scientific notation or standard form. Right? You want 2 significant figure, right, as that. This is 3 significant figure, 1.00 times 10 to the power 3. Or this is 4 significant figure. 1.000 and 10 to the power 3. Right? So it's important to write significant figure. This one is 1. This is not sure, not clear what instrument you use. Instrument used determine the number of significant figure. Right? Just like the length you measure using a meter rule is 0.900 meter. You cannot write as 0.9 because you can read up to this last significant figure, 3 decimal place, right? Which is 1 millimeter. So in this case, that is the correct way of writing. It's the wrong way of writing. Right? So in experiment, you do measurement, the breadth, the length, then you multiply them up. Right? One thing you remember is you choose the best instrument. This one, the error will be large. Same as this one, this will be larger still. So when you want to measure things that are small, you choose a vernier caliper. Right? If not, the percentage, this one will be, if you use meter rule, you have large percentage uncertainty, which we'll cover later on. Right? So you use a vernier caliper, you can read one more significant figure here, and one more significant figure here. Right? The uncertainty is usually the last one. So we take it as 0.01. 0.01 here too. So it's not necessary to use micrometer unless you want to measure thickness. Right? Thickness, you need to use micrometer to give you another significant figure. Right? Meter rule, smallest graduation is 0.1 cm, right? Or 1 millimeter. And if you measure 0.4 cm, you write as 0.4 cm. Vernier allow you one more significant figure. Right? The smallest graduation is 0.01. Micrometer, smallest graduation is 0.001 cm. They allow it to write one more decimal place. Right? So the reading for this part is you look at where the 0 is. This is 4, this is 3, so it's about 3.5, and then you look at where it coincides, 3.5. So 0.35 cm. Okay, or you can read it as in cm. It's 3.5, 3 point something. Check that. Where it coincides is 3.5. Okay? Cannot round it off because you use the instrument to measure. You must write to the number of significant figure. Right? So your measurement depends on the choice of the instrument. Right? We choose the instrument to get the acceptable precision. And our experiment technique must reduce as far as possible any uncertainty in the reading. Example, which instrument will you use to measure the length of 1 cm? Right? Vernier caliper or micrometer? Right? You use a meter rule to measure 1 cm is 0.1. Right? The smallest graduation or uncertainty is 0.1. Right? You use a vernier, you can read one more decimal place. So the smallest graduation is 0.01. Right? Micrometer give you a better precision. Right? Extra decimal place. Right? This is 1%. Sorry, this is 10%. Right? Which is very large uncertainty. This is only 1%, so it's acceptable. This one is smaller still. Right? You always take the uncertainty as the smallest graduation of the instrument. Okay, just like here. Smallest graduation is 0.001 cm. Let's try some workout. Right? Should be able to read your experiment. Should be able to read the milliammeter diagram. Shows the reading of an analog ammeter. Digital ammeter reading is the same as the reading on the analog ammeter. Okay, so you should be able to read. This is 1, 2, 3, 4. Right? So this is 1, and there are 5 divisions. 1 divided by 5. So the smallest one is 0.2. Right? So this is 1, 0.2, 0.4, 0.6, 1.6 milliammeter. Milliamp, sorry. 1.6 milliamp. Then you have to convert to micro times 10 times 1,000. Okay, no answer here. Just times. Reading is 1.6 milliampere times 1,000. Change to micro. So it's 1,600. This one is mainly for A-level student. Okay. You need to know how to do with your stopwatch for experiment. Okay. 3 minutes, 53.17 seconds. Complete the table with either the approximate instrument or the quantity measured. Right. Length 15 cm. You can use a meter rule. Right. Faster. Length of 4 cm. You can use vernier caliper. Diameter of 1.224 millimeter. You use a micrometer. Right. Voltmeter and ammeter to measure resistance. Spring balance to measure weight of an object. Level balance to measure mass. Angle, we use a protractor. Time, we use a stopwatch. Frequency of wave, can use a CRO or cathode ray oscilloscope. C for cathode, R for ray, O for oscilloscope. Question: how will you measure diameter of a wire? Use a micrometer. Measure at a few places along the wire and obtain the mean diameter. Right? To reduce the uncertainty. Right? For A level, you're required to write the 2 or 3 significant figures sufficient. Same with STPM. Correct to the measurement to the 3 significant figure. Okay. 1, 2, 3. So this is we have to add the 0 in to show that it's the same order of magnitude. Right? This one is 9.64. Right? Remember, we don't count the 2, 0, 3, 0 here. Only 7 as the first significant figure. So 7.65. 1, 2, 3. Okay, we cannot write this one as 784 because this one is only, in terms of magnitude, is too small. Right? This is 78,300. 78,360. So you have to write, if 3 significant figure, you have to write a 2 0 in. 4 and then put a 0 in. The size is the same. We cannot change it. We cannot make it smaller. Making graph into a straight line. Can be given an equation there. You want it to be in a straight line, you can rewrite that. Okay. F is a variable, M is a variable, K is a constant, 2 pi is a constant. So rewrite the constant to one side. So you can plot F against 1 over root M. Nothing there. Okay, so alternative, square it. Right? You can plot f over 1 root m. As I said, there's no answer. Your choice, but there's no answer here. So you square that, f square, this one becomes k, this becomes 4 pi square, and then this root m becomes m. So this is your constant gradient, right? So you plot 1 over m, f square against 1 over m, which is the answer is B. Right? If the light meter, that's a light meter, measures the intensity I of light falling on it, theory suggests that it varies as the inverse square of distance d. Right? So you should be able to recognize the graph. This is wrong. Right? It should go to infinity there. This is wrong because it should go to infinity there. So write out what is given. You should be able to read the question, inversely proportional, and rewrite it as an equation. Then compare to equation of a straight line, make it into a straight line. We plot I versus 1 over d square. So your answer is donkey. Right? This 1 over d square. So you should be able to recognize, right? You should be able to mesh, choose and mesh, which is what type of equation is one, what type of equation is this one, what type of equation is that. Right? Choose from the following the answer to the question. Okay, this is a rectangular hyperbola. Right? This is a parabola. Right? This is also a parabola. Okay, should be able to recognize our A-level and STPM student. Errors and uncertainty. Right? All the physical constants are tabulated in this book. You can find the library. Random errors. Estimate random error. That's what we are going to do. Then how to combine the quantity and the errors. Right? We won't be doing systematic error. Effect of graph, we won't be doing that. That one is for A-level. Okay, random error, measuring or length. Right? We can be sure for sure that it is between 25 or 26. But it's not 25 nor 26, it's between that. So we have to estimate the one more significant figure, which is it can be 0.5 or 0.4, can be 0.3. Right? It's just the best estimate that we do. So this is due to error is due to observer or need to estimate the last significant figure. Right? We are not sure. We cannot be sure. Right? You cannot say I say 25.5 millimeter is correct. No, I'm not sure the last significant figure. I know it's 25, correct, but 0.5, I'm not sure. That's why it's called uncertainty. Right? So it is a student find the accession due to gravity, right, repeatedly a few times to get 6 reading. Then how do we find the error? Speed reading, we find the mean value, right? Or add all of them up together and divide by 6. Right? There's a true value. 9.81 is true value. Right? So random errors that cause reading scatter. Right? There's the mean value. Some higher, some lower than the smaller value from the true value. So that's why we say scatter. Scatter equally about true value. Right? Some values are above, some values are below the true value, but it's not constant. Right? This one is below the true value. This is a true value. This is above the true value. Okay, so you should be able to define what is random error. The errors that cause reading to scatter equally about the true value. Example, measuring a length, measure a diameter of wire, room temperature. Why? What's the cause? Error due to observer. You are the one who have to estimate the last significant figure. Then can we reduce it or eliminate it? Can be reduced by taking more reading or the quantity and then finding the mean, or by plotting a graph and drawing the line of best fit, LOBF, line of best fit. Now you can never eliminate it. You can reduce it by taking more reading. Random error, different maximum possible error, uncertainty. We can use a small Greek alphabet, either small letter, delta, or triangle. It's also called delta. What is error? Deviation from the correct value. So we represent as delta L. Delta L we call uncertainty or random error. L is the measurement. Right? Example, 2.5 plus minus 0.1. Right? When we write as this, we are saying that the actual reading, right? The true length is between 2.4 and 2.6 cm. Right? 2.4 we get 2.5 minus 0.1, and then 2.6 we get 2.5 plus 0.1. Right? For one reading, a single measurement, right? Make sure you use your meter rule or ruler. You need to know the smallest graduation. If it is measured in cm, then it is 0.1 cm. Right? We have to make two readings. Where the zero is, there's uncertainty there. Right? You may say exactly you place there, but there's still uncertainty there. Right? So that's the initial reading, Ri. 0, it has an uncertainty there, 0.05 cm. Right? You read again, 2.5. Right? Don't need to be very particular. Right? It is about 2.5 plus minus 0.05 cm. That's the final reading. That's a piece of wood. That's a ruler. Every measurement that we do, we have to make two readings. Usually we forget about this one. And we have to read the initial one first. Then our error in reading, smallest graduation, half the smallest graduation. Right? If you read one side, half the smallest graduation. In this case, the smallest graduation is 0.1 cm. So you divide by 2 is 0.05 cm. Okay? That's where we got it from here. Here. Right? You want to show the length? Our final reading minus initial reading. So we subtract, we get 2.5 plus minus 0.1 cm. Right? We add these two errors, this uncertainty. Add them up. Let's get 0.1. Right? 0.05 plus 0.05, we get 0.1 cm. Right? Let's look at other terms. Right? That is the smallest graduation using meter rule. Okay? Smallest, so the uncertainty is 0.1. For example, 2.5 plus minus 0.1 cm. Okay, that's the uncertainty. Always one significant figure. It's already uncertain already, no point in putting two significant figures. Right? One is enough. Then this one decimal place, this one follow. Length follow as one decimal place. Right? In this case, it's two significant figures. Okay, remember, this one is telling us the length is not one single value because of uncertainty in the instrument. It is between two limits. We are sure between 24 and 26, 2.4 and 2.6, sorry. Right? Always remember, the uncertainty measurement is always the smallest variation. So don't bother to go and read, smaller than 2.55. Right? 2.6 or 2.5 is good enough. Right? You don't want to write so many significant figure here. Right? This one decimal place. So the answer should be also one decimal place. Right? Let's look at some terminology we'll be using. The length with its uncertainty delta L. Absolute error delta L or uncertainty. And we just want the positive value. Proportional error, we take our, right, or sometimes we call it fractional error, delta L over L. Percentage error, we just multiply by, we just take your, right, that's short form, right, just delta L over L times 100. That's a percentage error. Rules for combining error. Right? We can use simple method. Right? Example, sine y equals sine x. X is 30 plus minus 1. What is y? You should be able to calculate out. Right? Y, sine 30, that's your y. Right? Error in y. Well, you can try find the maximum value of y or the minimum value of y. Right? 30 plus 1. Right? You can use that principle in all your calculation. If you don't want to memorize rule, so use your calculator, sine 31, 0.515. Then subtract, is to subtract to get your error in y, uncertainty in y, the largest one, minus the mean value or the actual value. Okay, then we get 0.015. So it tells us that we want one significant figure, so we can write our value as 0.02, 0.5 not plus minus 0.02. Another example, right? We got R 4.00 plus minus 0.04. We want to find R square and its uncertainty. This is your R square that 4 square is 16. Then remember we want to find uncertainty. We want to find the largest value of this one or the smallest value of this one. So largest value of x, right? X is R square. So it's 4 plus that value. And then square that 16.32. So we subtract, right? Maximum minus the average value, we get 0.32. Round off to one significant figure, we can write our answer as 16.0 plus minus 0.3 cm squared. Okay, we can derive the rules. Right? You can use elementary method to calculate out, or you can use rule. Right? Example, A has uncertainty delta A, B has uncertainty delta B. Right? We want to D equals to A minus B. Right? D is the difference between A and B. And then we want to show that delta D is delta A plus delta B. Solution, same. We take the largest value, right? Or we can take D minus the smallest value, whichever you prefer. Right? Largest value. So largest value, right? To make this one large, A must be large, B must be small. Right? And then this is that value, A minus B. So largest value, A plus delta A minus smallest value, B minus delta B. And then this is still the same. Right? So we can see A minus A, no more, 0. Minus B plus B, also no more. Right? Minus, so we got answer is delta A, minus delta B is delta B. Right? There's no subtraction. Or another example, product, B product, multiply A times B. Right? We can show that we still have the same error, right? Same uncertainty. We want to show that delta P over P is delta A over A plus delta B over B. Right? We add the proportional error. Steps. Same thing. You want to find delta P. P max minus P. Right? How to get maximum P? Right? That's our P. Maximum use A plus delta A times B plus delta B. And P is A times P. Right? Expand it. A delta B and then we have A times B, A times B, and then B times delta A, and delta A, and then delta A and delta B. Okay, I simplify the step. So we take it off because of minus A delta B, right? A times B, subtract this one. Right? Remember, your delta A, delta B are small. So when you multiply them, it becomes smaller. So we can neglect that. Then we can divide. Right? We want to find delta P over P. So delta P we already calculated. Now divide P. Okay. P is AB. Okay, so neglect that term. We got these two terms there. That one divided by AB, which is your P. So we can separate them up. A and A cancel. We got delta B over B. B and B cancel. We got delta A over A. Right? So either you can, in all calculations, you can use elementary understanding of errors, or you can use rule. Right? Adding or subtracting, right? As a sum, A plus B, or different, A minus B. Right? We just add the error. We want the uncertainty in the sum or uncertainty in the difference, we add the absolute error, delta A plus delta B. And each of them got uncertainty, delta A, this one got delta B, add them up. Right? Multiply or divide, same. Multiply P product, quotient A divided by B. So then we just work with proportional error or fractional error. Delta A over A plus delta B over B. Right? Or we can multiply by 100 on left hand side and right hand side. Then we can also do it as percentage error in P or percentage error in Q equals to percentage error in A plus percentage error in B. Okay, it's just to remind you, where you sum, you add the uncertainty, get the uncertainty in S. Or subtraction, the same thing. Right? You want to find uncertainty in D, you just add the uncertainty in A, uncertainty in B. Right? Or multiply, the same thing. We each of quantity, this is fractional error. Delta L also has fractional error. Delta B also has fractional error. And we just add them up. Right? Example, this one. Area of rectangle, L times B. Right? Delta L or delta B. Sorry. Fractional error in A equals to fractional error in L plus fractional error in B. Or as I say, you multiply by 100. Right? Then you call it percentage uncertainty. Percentage error, you add a percentage error. Right? So if it's L squared, same thing. Right? You can write the same thing and then learn from it. Right? We get 2 delta L. So that 2 is because of that square. Right? So we can repeat it for to the power 3, same thing. Right? So we can have our general summary. 3 times percentage uncertainty in A, if you want to find percentage uncertainty in Y. So if it's Y equals to A to the power N, take the N down, and then this one is the proportional error. Right? So we can use percentage uncertainty. Okay, just now we are done for function. Okay, just to summarize for you, we can use this basic method. Find the maximum minus the minimum, largest value minus the average value, or you can use average value minus the smallest value. Or I can measure using rules. Right? AS you find easier to use rules. Right? This time one question. So, suppose a student measures the length as 20.0 plus minus 0.1. Find the proportional error. It's just to get you familiar to the terms used. Proportional error, delta L over L. So it's 0.1 over 20.005. Percentage error in L. Right? You just multiply what you have calculated times 100. So it's 0.5%. Right? Experiment. Smallest graduation you must be able to read. In this case, is 2 cm. So uncertainty in reading is one reading, you divide by 2, we get 1 cm. As I say, we hardly use that. Usually we use a measurement. So we use the smallest graduation. We use this one as our uncertainty. So our initial reading, 20 plus minus 1. And final reading is 230, 240. So each of these is 20, 20, 40, 60, 80, 100, so 230. Sorry, not 20. 2, 4, 6, 8, 10. Okay, so it's 300, 236. Okay, it's 10, this 2, 4, 6, it's 230, 236 plus minus 1 cm. Right, that's the initial reading, that's the final reading. Right, if you put a pebble in here, and the volume of pebble, you just subtract them. 236 minus 20 is 216. Add the uncertainty, you get 2. Right? You can test yourself just to know, right, how to identify which is S, which is delta S. You should be able to bring down yourself. Delta S, proportional error, delta S over S, percentage, you just times your 100. Right? Proportional error times 100. So it's got 2%. Okay, that's our S. X equals to S plus B, and B as its uncertainty. Right? So just to reinforce it in, so you know how to identify that is your delta B. Right? That's your delta S. So delta B is 0.3. Percentage error in B is delta B over B times 100. Delta B is 0.3. 0.3 divided by 20 times 100. So it's 1.5 cm. Right? X is a summation of S plus B. So we just add the error by 2 plus by 3. Plus by 3, we get 0.5. Okay. Percentage uncertainty in X. Okay, percentage uncertainty in X. The same thing. We have, this one we calculated previously. Calculate our X first. Okay. Our X is S plus B. S plus B, 10 plus 20 is 30. So percentage uncertainty in X is delta X. Delta X is 0.5 over X. X is 30 times 100. Get 7%. Okay, test yourself. Try this question. It's a product. P equals to S times B. What is the percentage uncertainty in P? Right? This is given. Percentage uncertainty in S is given. Percentage uncertainty in B is also given. So we add the percentage uncertainty as well. It's multiplied. So you just add them up. Percentage uncertainty. Percentage uncertainty in S. Percentage uncertainty in B. Is 2.5. Percentage we can leave it as two significant figure. Only absolute one significant figure. Okay, so let's summarize for you the rules that we can use. Right? This one we have done before. Right? You can use answer. You can use your A equals to L square. You can find your A, 4 square, 16. Then if you use the rule, delta A over A is 2, take a 2 down there. L is delta L over L. Right? A is 16. 2 delta L, that's your delta L, that's your L. Use your calculator, take the 16 over, calculate out, remember one significant figure, then that's how you will write it. Right? You will do experiment. Right? There's a spring, there's a meter rule. So that's the initial length, initial reading or original length. Right? 10.00 plus minus. Right? Uncertainty in reading. And you have a final reading, you read again. 12.50 plus minus 0.05 cm. Then you want to measure E, the extension. Right? Subtraction, you subtract the final reading minus initial reading. You get 2.5. Right? You add the uncertainty, 30 subtraction. Delta L, that's your delta L, that's also your delta L. Add them up is 0.1 cm. Right? One decimal place. Okay? You can write your answer. Okay? Another example. Percentage uncertainty in C is 5%. Percentage uncertainty in B is 2%. Percentage uncertainty in A is 3%. You want to find the percentage uncertainty in F. Okay? Remember, this is product and power. So you should be able to write percentage uncertainty in F equals to percentage uncertainty in A. Because of the square, it times 2. Because of the cube, times 3. Uncertainty in B. And then we got percent uncertainty in C. No power. And put in your value. 2. Then uncertainty in A is 3%. Then this is 3. Percentage uncertainty in B is 2%. And then percent uncertainty in C is 5%. Add them up. Okay. Sometimes at A level, they may ask this type of question. Number of significant figure. Right? Writing correctly to the number of significant figure, especially when you do the experiment. Right? The thing to remember is uncertainty must be written to one significant figure. And the quantity, in this case, is the speed, will follow. Right? So percentage is given you 3%. You must be able to read delta V over V times 100 is 3%. Delta V, well, you can round it off, doesn't matter. 327 times 100. Because 3% is quite high. 3% is, right? We take 3% of this one. You don't need to worry about the decimal place already. You can use that. You can use the real number if you want to. It doesn't change much. I can find your delta V, 9.8. Right? As you take this across, take 100 down. 9.8. Remember, you want one significant figure, you have to round off to 10. Right? So you should write as 330 plus minus 10. Not 327. Because you can read up to the 10th tag here, which is here, not here. Okay. Or you can write in scientific notation, which is easier to see. Right? That's one decimal place, that's one decimal place. Answer is donkey. Right? So you should be able to correct the number of significant figure. You need to remember, uncertainty is one significant figure and quantity must follow. Right? Not one significant figure, but on the one significant figure that you have decided. Example for this one, right? 98 has to go to 100. So you should write as this one is 300 because 100. 300. This one should be 10. So it's 330. This one is 9. Right? So you can drop one decimal place here. You can read up to 327 plus minus 9. Right? This one should be 0.4. So this one can read to one decimal place. This one can read to 2 decimal place. So this one should be 2 decimal place also. Okay. Okay, I think we will end the class for today. You can try this one if you want to. Okay, thank you.